I'm Anil Kumar. Welcome to my series on graphing trigonometric functions. In the very first basic video, we'll take up these 5 examples. So we'll begin with the function y equals to sine x. Amplitude will be changed and then we'll see how the graph changes. And then we'll again work with sine x, but this time we'll do horizontal, rather the time period changes, horizontally compressed or expanded. So we'll take different conditions. And then we'll reflect the sine graph and do translation. D here plus t means vertical, up and down. And then we'll work with cosine function and tan function. In part 2, we'll actually do sketching with graph. And this time we'll just make rough sketches to understand the concept. To begin with, let's just think about the sine and cosine functions first. So I'll just sketch these 3 graphs with which we'll be working. Let me draw it here itself. So when we say sine function, we're trying to say that the function is kind of like this. The cosine function is kind of like this. And the tan function has vertical asymptotes, and it looks like this. Right? So I'm not sketching the basic functions, but we are more discussing about how they look like after transformations. So we are not really focusing on how to sketch the very basic function. This one is sine x for us. We know these zeros are 3 within a domain of 2 pi. Right? Maximum and minimum values are plus and minus 1. For cos x, maximum and minimum being plus and minus 1, this is 0. And the zeros for cos x are at pi by 2 and at 3 pi by 2. One period is 2 pi for cos x. Right. As far as the tan x is concerned, we have vertical asymptotes as minus pi by 2 and pi by 2. The period for tan x is pi. Period for sine x, as you can see, is 2 pi, same as cos x, correct? Now let's begin with the transformation and understand how to sketch these transform functions. So first one, let's take up cosine x, right? So I'll sketch slightly bigger graph here for clarity. And we are only sketching one sine wave. These are periodic functions. So, so when you kind of sketch it, you should see that it is kind of periodic functions. Let me sketch like this, just to show you that these are periodic functions. And so we should actually think about showing them as a wave which goes for the domain of x real numbers, right? Now, this particular function is y equals to sine x, which I have drawn now, right? Here, as we did earlier, this is at 0, this is at pi, and this one is 2 pi. Maximum value being 1, and minimum value being minus 1. Now, if I have to sketch for a equals to 0.5, it means what? Well, let me sketch in a different ink the second function, which will be y equals to, let me write down, y equals to 0.5, 0.5 sine x. Now, if amplitude is 0.5, we mean that half, right? So both maximum and minimum will not be now 1 or minus, will be now, maximum will be half, minimum will be minus half. That's all. So it is vertically compressed by a factor of half. So it'll be kind of like this. Do you see that part? Right. So that is what will happen to the graph. I could sketch it as this. All the zeros will remain at the same point. They are not going to change. Do you see this? They are not going to change, but the values will reduce to half. So for this particular function, which is y equals to half of sine x, the amplitude will become half, right? So this will be here, you can say this portion here will be minus half. You're getting the idea, correct? Now if I say that the amplitude is 2, if I say that the amplitude A equals to 2, then the equation becomes y equals to 2 sine x. Now 2 sine x basically means that instead of 1, it will get multiplied twice. Instead of minus 1, it will be at minus 2. However, these points will all remain the same, right? So what we have is these 5 critical points to sketch. So now the function will be, so here also we'll have it at minus 2. Let's say this is at 2. So the graph will now be kind of like this. So these are rough sketches, but they give you a fairly good idea about what we are getting into, right? So kind of like this. So this is the graph for y equals to 2 sine x. So what we see here clearly is that A is the amplitude, and it really gives the value as vertical stretch. By a factor of A, right? So if A is greater than 1, we see it as a stretch, but if A is less than 1, we see it as a compression, correct? So if A is, let me say absolute value of A is less than 1, then basically it's a compression. So I hope that part is absolutely clear, right? So now we'll move on and see what happens if we do something with the x part of it. That is to say, what is going to be the effect of k in the equation y equals to sine kx. So we'll take up 3 values of k, which is 0.5, which is as good as half, right? 1 and 2, and then see what really happens when the k value changes and all other things remain the same. So now let's once again sketch the sinusoidal function. Okay, now so what I will do here is first sketch with okay. So what we've done here is that we have sketched the function, which is, let me write in the same color. This color is for y equals to sine x. So that means the k value is basically 1. So we have sketched this graph now. Now we will see what happens when we do k as 0.5 or we change k to 2, right? So these are the points which are critical points for us. So the maximum, 0, minimum, and back one cycle, right? So this is 2 pi for us. This is pi. Here we have pi by 2, and this is 3 pi by 2. That is indeed 0. This is plus 1, and we have this as minus 1. So I hope you are getting the concept, correct? So let me first try with what happens when we write k as 2. So if I have k equals to 2, then the equation becomes y equals to sine 2x. Now as soon as the equation becomes y equals to sine 2x, the time period t will become 2 pi by this value 2, which is basically pi. So for this particular condition, what we notice is that everything compresses halfway, correct? So what really happens is that we have 2 waves. So we have 2 sine waves. Which could be shown like, so that all these points, they come halfway. So this comes halfway, it comes to this point. This 0 comes to pi by 2. 0 remains 0, and 2 pi actually comes to pi, right? So this point shifts to this particular position. So one wave now is only this much, right? Similarly, the other half, now the second wave, so we get actually two waves in this particular thing. So this is my first wave within 0 to 2 pi, and the second wave is ending here with the zeros, 3 pi, 2 pi, kind of like this. So that becomes two waves in 2 pi. So that is sine 2x. You get an idea. So it is horizontally compressed. So if it is k equals to 2, then it is horizontally compressed by a factor of half. You get an idea. So that is what happens when we are talking about 2. Now let's consider the case when we'll take the value as k as half, right? So now let's think that k equals to half. So the equation becomes y equals to sine of half x. Now that really means we have horizontal stretch by factor of 2. So this time the wave actually stretches and only half the wave is up to this point. So this time the wave will be kind of like this. Do you understand? So we have a wave which is like this. So you see only half the wave in up to 2 pi and then rest like this. Correct? So I have less space here. However, you appreciate this is just the half wave. So the time period t will now be not 2 pi but 4 pi. That is 2 pi divided by half, which is equals to 4 pi. So that is what happens when the k value reduces. You get an idea. So it expands horizontally. So that is how it will look like on a graph. Right? So now let's move forward and take up more examples. Now we are going to take up two examples, one with y equals to minus. This minus means reflection on the x-axis, sine 2x. For d value of minus 1, so we'll make one graph with this equation, the other graph with y equals to minus sine 2x plus 2. So basically now we will see vertical translation. So these are two things which we are going to notice. One, we are going to see reflection on x-axis. Then this 2, as we saw in the last part, means horizontally compressed by a factor of half, or time period is equal to 2 pi by 2, which is only pi. So it is horizontally compressed by a factor, right? Now then we'll see the effect of d. So if d is equals to minus 1, it is 1 unit down, and if d is equals to 2, it means 2 units up. So that is its vertical translation, right? So that basically gives us vertical translation. So to sketch the graph, let's sketch all the graphs in one go here. Amplitude being 1, right? So we'll just maintain the amplitude as 1. Axis for the default is sine x. So the default wave sine 2x, where d is 0 could be like this. Let's say this. Okay, so what I've sketched here, this wave is basically sine 2x. So this green wave is sine 2x, where these pi are 0. Now the time period for sine 2x will be pi, right? So that is one wave sine 2x. This is definitely now pi by 2. So first part is, let's sketch sine 2x. So the time period becomes, instead of 2 pi, becomes just pi. So we are horizontally compressed by a factor of half. Now, minus means it is reflected. So that minus means it goes in this fashion. So it kind of like this. So it gets reflected. And this is what you get here, right? So this curve here, basically, what you see here is minus sine 2x. So that is the reflection part. So that is reflected on the x-axis. Correct? Now, let us see what happens with d of plus 2 or d of minus 1, right? So if d is minus 1, then this axis moves at minus 1. So this is minus 1 for us. So we have the axis right there. So the whole wave shifts 1 unit down, right? So this is d equals to minus 1, correct? So this pink graph which you see here, instead of being starting at 0, it comes down to minus 1. This is minus 1 for you. Right, so all these points, they move 1 unit down. So this point will be here, that point will be right there, and the minimum will be at minus 2, right? So minimum will be at minus 2. Similarly, the other point which was at plus 1 will now move to 0. So that is how these points are going to move. So these are our new points. Do you see that? So joining them, I get my graph, which is, so this is here, right? So this graph which you see is for the graph of minus sine 2x minus 1. So that is y equals to minus sine 2x. So everything shifts 1 unit down. So the maximum value becomes 0, minimum becomes minus 2. However, if we use the value of ds plus 2, in that case, this pink graph, which is of minus sine 2x, shifts 2 units up. So it will be like axis will be here at d equals to 2. Since the amplitude is 1, so the maximum will be somewhere here, minimum 1 unit down. So the graph which you see here will start from here, go to this place, correct? And that comes back. This is the maximum, right? And then it comes down. So what you see is a graph which is kind of like this. I have slightly shifted, but that is how it is going to look for the graph of minus sine. So let me write down y equals to minus sine 2x plus 2. So the effect of d is basically shifting the wave up and down. The effect of minus is to reflect it on the x-axis. So I hope you're getting an idea, right? So this is the x-axis and that's the y-axis. So that is how we take care of vertical translations. This time we are going to sketch graph of y equals to 3 cos pi by 2x. Now, from here, we can write down that the amplitude is equal to 3, right? I wrote 2 a's. Now, what is the time period? Time period normally is 2 pi. Since k is pi by 2, it is 2 pi by pi by 2. Is it okay? So that gives you a time period of 4. So the time period is 4 here. X is at, there is no vertical translation, so x is at y equals to 0. So to sketch this graph, the cosine function, what we could do is, we could sketch something like this. Where the one particular wave is up to here, right? So what you notice here is that, let me just extend this. Time period is 4. So this full wave up to here, this is 4, right? So this point is at 2. This point is half of 2, which is 1, and here it is 3. The amplitude being at 3, and this minimum will be minus 3. Does it make sense? So as you know, they are periodic functions, so it will kind of continue. So I'm interested actually in showing you one wave. So that becomes one wave for y equals to 3 cos pi by 2x. Does make sense to you, right? So that is how it is going to look. Now in part 2, we will see transformation of such waves. Now cosine function starts with the maximum and ends with a one wave, ends with the maximum as shown here, and it has 2 zeros in one cycle. Correct? Now let's take up the tan function. Now the function which we need to graph is y equals to tan half of x plus pi by 2. So let's begin by graphing the basic tan function, which looks like this. So it has vertical asymptotes at pi by 2, right? So the graph of the function is normally like this. This goes through 0. And these are the vertical asymptotes. So this is minus pi by 2. This is plus pi by 2. That is 0 for us. Now this is the graph for y equals to tan x. Now when we say tan of half x, that means horizontally stretched by factor of 2. Correct? So that is the first step. It is horizontally stretched by a factor of 2. So what really happens is that these vertical asymptotes now will move outwards. Right? So instead of having these vertical asymptotes at pi by 2, we'll have them at pi. So let me show you here. So we're kind of going in steps so that, you know, later on, when we incorporate many transformations together, we don't have difficulty, right? So that is what it means. So now I'm going to sketch the horizontally stretched function. So all these points, the critical points, they'll just move away, right? So this point moves to that point. So what we get here is kind of like this. Do you see that? So that becomes the graph for y equals to, let me write here, y equals to tan of half x. Correct? So it is horizontally stretched. Now let us incorporate horizontal translation of pi by 2. So the last step here is pi by 2, which is translate pi by 2 units left. So let's do with a different ink. So to translate pi by 2 left really means that this vertical asymptote will now move pi by 2 here, so we'll get it right there. And this also moves pi by 2 to the left. Okay. So let me just okay. So instead of being at pi, now it will be rather minus pi. It will be minus 3 pi by 2. So it will move out here at minus 3 pi by 2. Correct? So now the graph, the 0, will now move to by pi by 2 to the left. And so what we have is a graph which is kind of like this. Do you get the idea? So that's our final graph, which is tan half x plus pi by 2. You get an idea, right? So that is how we should draw the translated version of tan graph. But in this series, what you learned is how to systematically graph and get the result. Now in part 2, we'll see how the points, the image point change with the transformation, and we'll be in a position to draw fairly accurate graphs. So this part is basically to give you an idea of how these graphs get transformed and how they basically look like. I hope that helps. It gives you a bigger picture. Now in next part, we'll look into transformation of points, and we'll look into image points to draw accurate graphs on a graph paper. I hope that helps. Feel free to write your comments and share your views, and if you like and subscribe to my videos, that'd be great. Thanks for watching.